Namaste, my friend, and welcome to JEE Chemistry with Typical Monk. This is Class 1, and we begin at the very beginning, the mole. Now, here's a beautiful problem to sit with for a moment. A single drop of water holds more molecules than there are stars in our entire galaxy. Atoms are impossibly small and impossibly many. So how does a chemist ever count them? When Sarah first heard this question, she laughed and said, "Nobody could count that high in 1,000 lifetimes." And she is right. Which is exactly why chemists invented something wonderful, a way to count without counting. And in JEE, this one idea grows into multi-step numericals worth real marks. Today, one idea at a time, we build the single most important tool in all of chemistry. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the mole itself and Avogadro's number, chemistry's own counting unit. The idea every other calculation stands on. Second, molar mass, the mole bridge, and percentage composition. How much a mole weighs and how much of a compound is which element. Third, the difference between the empirical formula and the molecular formula, the simplest ratio versus the real molecule. Fourth, stoichiometry, the limiting reagent and percentage yield. How to predict exactly how much product a reaction can give, which reactant runs out first, and how much is really formed. And fifth, the JEE drills, assertion and reason, match the column and the numericals, so that everything you learn today you can also score with. Ready? One idea at a time. Let us start with the problem itself. Atoms are far too small and far too many to count one by one. Even if David counted 1 billion atoms every second of his life, he would not finish a single grain of sand. So chemists do what shopkeepers do. They count in bulk. That bulk unit is the mole. And here is the heart of it. 1 mole equals 6.022 into 10 to the power 23 particles. Recall this Avogadro's number. Do not let the size frighten you. It works exactly like the word dozen. When Sarah buys a dozen bananas, she does not count 12 every time. The word dozen means 12 always. In the same way, the word mole means 6.022 into 10 to the power 23. Always. A dozen eggs, a dozen atoms, a mole of eggs, a mole of atoms. Same idea, bigger number. Now, the magic of the mole is that it connects counting to weighing. 1 mole of a substance weighs its molar mass in grams, a number that is numerically equal to its atomic or molecular mass. So 1 mole of carbon weighs 12 grams. 1 mole of water weighs 18 grams. You weigh the substance on a balance and you have secretly counted its particles. And there is one more gift. 1 mole of any gas, hydrogen, oxygen, carbon dioxide, it does not matter which, occupies 22.4 liters at standard temperature and pressure. Number, any gas, the same volume. Sit with that for a second. It is one of the most examined lines in this chapter. Look at this diagram carefully, because it is the map for every numerical in this chapter. In the middle stands the mole, like a bridge with 3 roads leading away from it. The first road connects grams to moles. If you are holding a mass, divide by the molar mass, and you arrive at moles. 36 grams of water divided by 18, 2 moles. That's simple. The second road connects moles to the number of particles. Multiply your moles by Avogadro's number, 6.022 into 10 to the power 23, and you know exactly how many atoms or molecules you hold. The third road connects moles to gas volume. Multiply your moles by 22.4 liters, and you have the volume at standard temperature and pressure. And now, the master trick, the one habit that solves this entire chapter. Whatever the question gives you, whatever it asks for, always convert to moles first. Stand on the bridge, then hop across to whichever side you need. Lisa used to jump straight from grams to molecules and kept slipping. The day she started walking through the bridge, grams to moles, moles to particles, she never got one wrong again. Now let us read the formula, the way a chemist reads it. First, percentage composition, the mass percent of each element in a compound. and you can read it straight off the formula. Take water, 18 grams per mole, of which 16 are oxygen. So water is nearly 90% oxygen by mass. The formula quietly tells you what the compound is made of. Second, the empirical formula. This is the simplest whole number ratio of atoms, not the real molecule, only its skeleton, its simplest recipe. Third, the molecular formula, the actual count of atoms in one real molecule, and it is always a whole number multiple of the empirical formula. How do we find that multiple? We call it N. N equals the molar mass divided by the empirical formula mass. Watch it work on glucose, and this example alone can fetch you a JEE question. Glucose has the empirical formula C, 2O1 carbon, 2 hydrogens, 1 oxygen, with an empirical mass of 30. But the molar mass of glucose is 180. 180 divided by 30 is 6. So the molecular formula is 6 times the empirical C6, 1206. The skeleton multiplied by 6 becomes the real molecule. Now the JEE twist, a 4 multi-step numerical solved slowly, the monk's way. The reaction, nitrogen plus 3 hydrogen gives 2 ammonia. We are given 28 grams of nitrogen and 10 grams of hydrogen, and in the actual experiment, 27.2 grams of ammonia were collected. JEE will ask you 3 things at once: the limiting reagent, the percentage yield, and how much excess reactant is left. Step 1. Cross the bridge to moles. Nitrogen, 28 grams divided by a molar mass of 28, 1 mole. Hydrogen, 10 grams divided by 2, 5 moles. Step 2. Find the limiting reagent. The equation says 1 mole of nitrogen needs 3 moles of hydrogen. We have 5 moles of hydrogen, far more than the 3 required. So hydrogen is in excess, and nitrogen runs out first. Nitrogen is the limiting reagent. Step 3. The theoretical yield. 1 mole of nitrogen gives 2 moles of ammonia, and ammonia's molar mass is 17. 2 times 17. 34 grams of ammonia is the most we could ever make. Step 4. The percentage yield. The experiment gave only 27.2 grams. Percentage yield is actual over theoretical times 100. 27.2 divided by 34 times 100, 80%. Step 5. The excess leftover. Nitrogen used only 3 moles of hydrogen. So 5 minus 3 leaves 2 moles of hydrogen unreacted. That is 4 grams of hydrogen still sitting in the flask. Limiting reagent, theoretical yield, percentage yield, and leftover excess. 1 reaction, 4 JEE answers. Now, concentration, how much solute is dissolved in how much solution. 2 cousins live here, and JEE loves to test whether you can tell them apart and convert between them. The first is molarity. Written with a capital M, moles of solute per liter of solution. But notice its weakness. It is built on volume, and volume expands when you heat it. Warm the solution, and the liter grows, so the molarity drops. Molarity depends on temperature. The second is molality. Written with a small m, moles of solute per kilogram of solvent. And here is its quiet strength. It is built on mass, and mass never changes with heating. John once asked, why do we even need 2 units? This is why, when temperature varies, molality stands firm while molarity drifts. Third, the mole fraction. The moles of one component divided by the total moles of all components, a pure ratio with no units, and for very dilute solutions, we count in parts per million. And fourth, the JEE link you must not miss. Molarity and molality can be converted into each other if you know the density of the solution. Keep the density formula ready, because JEE hides one full numerical in exactly this conversion. Now sit up straight. These 5 lines are what JEE actually asks year after year. 1. A mole is 6.022 into 10 to the power 23 particles, and the molar volume of a gas is 22.4 liters at standard temperature and pressure. Memorize both cool. They should come to you faster than your own name. 2. JEE numericals chain the steps: limiting reagent, then theoretical yield, then percentage yield, then how much excess is left. Learn the chain once and you own every stoichiometry question. 3. Molarity changes with temperature. Molarity does not, and you must be able to convert between them using density. 4. The empirical formula is not the molecular formula. Molecular equals N times empirical. Find N from the molar mass. Remember glucose where N was 6. 5. Numerical answers must carry the correct significant figures. Your answer can never be more precise than your least precise piece of data. In the numerical section, precision is marks. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. Molality is preferred over molarity when the temperature of an experiment varies. Reason, molality is independent of temperature. Think like Sarah. Check each statement on its own. Then check the connection. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. Molality is preferred precisely because temperature cannot touch it. Both true. Reason explains. Option A. Second one, assertion. 1 mole of any gas occupies 22.4 liters at standard temperature and pressure. Reason. 1 mole contains 6.022 into 10 to the power 23 particles. Both statements are true, no doubt. But pause. Does the number of particles explain the volume? No. The molar volume comes from Avogadro's law. Equal volumes of gases hold equal numbers of molecules, not from the size of the number itself. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. 2 true statements that simply stand side by side. Third one. Assertion. 16 grams of oxygen gas contains 6.022 into 10 to the power 23 molecules. Reason. The molar mass of oxygen gas is 32 grams per mole. Check the reason first. 32 grams per mole. True. Now the assertion, if a full mole weighs 32 grams, then 16 grams is only half a mole. So it holds only half of Avogadro's number of molecules. The assertion is false. The reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. Avogadro's number 6.022 into 10 to the power 23. The count hiding inside every mole. The molar volume of a gas at standard temperature and pressure, 22.4 liters. Any gas, always. Molarity, moles of solid per liter of solution. Litera, so it drifts with temperature. And molality, moles of solute per kilogram of solvent. Kilogram, so temperature cannot shake it. If all 4 came to you before the reveal, the bridge is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Molality is independent of temperature. Hold your verdict. Statement 2. The molecular formula is always the same as the empirical formula. Think of glucose before you answer. Statement 3. 1 mole of carbon-12 weighs exactly 12 grams. This is, in fact, the very definition the mole was built on. So, how many are correct? 2 statements, the first and the third. Molality truly ignores temperature, and carbon-12 truly anchors the mole at 12 grams. But the second one falls. The molecular formula is N times the empirical, and N is only sometimes 1. Glucose, with N equal to 6, is the counterexample you should carry into the exam hall. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. The limiting reagent is whichever reactant has a smaller mass. It feels so natural. Less stuff runs out first, no? David believed this for months. But here is the truth. The limiting reagent is decided by the smaller mole ratio relative to the balanced equation, never by mass alone. Remember our worked example. Hydrogen had only 10 grams against nitrogen's 28, yet hydrogen was the one in excess. convert to moles first always, then compare with the equation. Myth 2. Percentage yield can be read straight from the reactant masses. If you started with more, you must have made more. No. The truth, percentage yield, is the actual amount divided by the theoretical amount times 100, and the theoretical amount comes only from the limiting reagent. In our example, 34 grams was theoretical, but the flask gave only 27.2, 80%. Never guess the yield from the starting mass. Time to test yourself, rapid fire, and today it is all numbers. Here is the rule. I ask, you answer in your head before the reveal and spell the number to yourself. No pen, no paper, just the bridge you built today. Question 1. How many moles are there in 36 grams of water? Molar mass of water is 18. 36 divided by 18, 2 moles. Question 2. How many molecules are there in 0.25 moles? A quarter of Avogadro's number, 1.5055 into 10 to the power 23. Question 3. From 1 mole of nitrogen with hydrogen in excess, what is the theoretical mass of ammonia? 2 moles times 17, 34 grams. Question 4. If the experiment gives 25.5 grams of ammonia against a theoretical 34 grams, what is the percentage yield? 25.5 over 34 times 100, 75%. And question 5. The thinker. In nitrogen plus 3 hydrogen gives 2 ammonia, you have 1 mole of nitrogen and 2 moles of hydrogen. Which one is limiting? Careful. 1 mole of nitrogen demands 3 moles of hydrogen, but you have only 2. This time, hydrogen runs out first. Hydrogen is the limiting reagent. If you quote that reversal, you have truly understood today's class. Let us gather the whole class in one slow breath. The mole is chemistry's counting unit. 1 mole is 6.022 into 10 to the power 23 particles, just as a dozen is 12. The mole bridge links mass, particles, and gas volume, and the master habit is to always go through moles first. 1 mole of any gas is 22.4 liters at standard temperature and pressure, and the molar mass in grams is exactly 1 mole on your balance. Numerical formula is the simplest ratio, and the molecular formula is N times the empirical. Glucose C612O6 with N equal to 6. And the G numerical chain, find the limiting reagent, then the theoretical yield, then the percentage yield, then the excess reactant left over. And next class, we go inside the atom itself. The structure of the atom, Thomson's model, Rutherford's gold foil, Bohr's orbits, and the beautiful hydrogen spectrum. Do not miss it. And so, my friend, we have taken the first step. It may have looked like just one number and a bridge, but understand this. The mole unlocks every calculation in chemistry, every equation you will ever balance, every concentration you will ever compute, every numerical G will ever throw at you. They all walk across the bridge you built today. Sarah, David, Lisa, and John all started exactly where you are right now with this one class. Be patient with yourself. Revise the bridge tonight, once, slowly. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you inside the atom.